Once you obtain data by doing your experiments, then you have to do something with that data. And that's when you try to organize your data, maybe graph them, and do some analysis on them. One of the first thing you'll be doing is to, with the data, is to put it in a table because that's a way to organize your data. A table includes a title. Well, actually, these examples don't have a title, so there should be a title at the top of what this data is representing. There should be column headings, so these are called columns, right? And so there should be headings at each heading of the column. So in this case, you have this column is going this way. You have the heading for that, and then you have labels for these columns, although they're pretty short, for on the top over here. Okay, and there should be units involved in somewhere. Whether so, in this case, the units are in milligrams per liter, and that applies to both nitrates and phosphates. So you have the units over here. These are the numbers of butterflies. So these are actually units, the number of butterflies in this case, and that represents the number of butterflies. And these represents the carbon dioxide bubbles. So that will be the units for that. In this case, they're using the percentage as a unit. So it should always be indicated somewhere. Sometime it's in each of the column headings. If the units are different, or at the top, or somewhere in the description in the columns should include what these numbers mean, because numbers by themselves don't have a meaning, right? You have to have units with them. Independent variables usually make up the first columns so a typical table is something that looks like this, where these are the independent variables and then these are the results. So these will be your dependent variables. Okay, depending on the data and depending on the page in which you're trying to put it on, you may put it like, this way, in which case your independent variable is on across the top like this, right? So number of butterfly that's on these things are dependent on the type of food that you provide them. So these are your independent variables, and these are your dependent variables. In this case, you have the independent variables over here, whether nitrates or phosphates. No, actually, the independent variables, the sites, right? You're looking at 3 different sites, and you're looking at the concentration of nitrates, and also you happen to be also looking at the concentration of phosphates in those sites. So the independent variable is these sites, and then the dependent variables are these values. In this case, looks like the independent variable is time, because depending on how much time that it has elapsed, the amount of number of bubbles released by the yeast is going to be different. And you just happen to be looking at 3 separate test tubes in that one. Okay. So dependent variable is basically the data that fills the table. I'm just going to very quickly go through different types of graphs. There are pie graphs. They are very good at showing proportions. Oftentimes you've seen it as percentages, but depending on the pie chart, you might actually have numbers. But just make sure all these numbers, if it's a percent, it should up to 100%. And if it's the absolute numbers, it should add up to whatever is the whole. Bar graphs are good for when your independent variables are in categories. So, and they're discrete sets of data. So in this case, you have pollution concentration, and you have 3 sites, and these 3 sites may not necessarily be related to one another. So they might not be continuous. You might have one site over here, one site over there, another site over here, and they're not really related to one another, and they're not continuous, in which case you have to put it in a bar graph, right? A bar graph indicates that each one of these are independent of each other, right? And you're looking at, and you're just comparing the values between them. Line graph is, you use them when your independent variable is continuous or some kind of a numerical. Usually it's time. So when you have time on the x-axis, so if you're looking at how things change over time, that generally is going to be a line graph. Distance too. So if you're looking at something over distance, and so let's say there's a pollution discharge on one end, and then you're looking at how things are affected along, away from where the pollution is, that's going to be a line graph as well. So all of these examples are with independent variable being time, right? And again, make sure the units are there, right? So the time is it. So this one is days, this one is years, this one is also years, right? And then on the y-axis, which is basically the units and the numbers for the dependent variable, there should be some indication of what these numbers represent. So in this case, this is actually a very bad graph because it doesn't tell you what it is on this side, but from the title you can tell that that's the grade point average. You really should just say grade point average right here. This is alligators for kilometers of shoreline. Right, those are the units. So these values inside represents the number of alligators per kilometer of shoreline. Histogram is a special type of graph that shows frequency distributions. So on this axis, you have the size, and then you have number of muscles, and you're suspecting that the frequency of these muscles or number of muscles that you'll find is going to depend on the size. You're going to tend to find certain muscles, a lot of certain size muscles, and then you're going to find fewer of really big ones and really small ones. So this is your independent variable here. And it should technically be a line graph, but because but histograms are traditionally shown as bar graphs, and then you usually draw a smooth line over it. Okay, it's a bar graph because you're counting the category. So you're looking at a muscle that's between 50 and 25 and 30 over here, and this is how many you had, right? And you have discrete data, but it's actually continuous data, so that you draw the line through it. Scatter plot shows a relationship between two variables, and what it does is it shows that there is some relationship between them, or maybe there isn't a relationship between them. But even if there is a relationship between them, it really doesn't tell you the cause and effect. You need to do more experiments to determine that. So in this case, you're looking at the price of cars here, right? So you have cheap cars on this end, like more expensive cars on the other end, and then this is the top speed. So it looks like the more expensive the car, the higher the top speed. But is it maybe that, when you have a top, speed that's really high, tend to make the cars more expensive. So you don't really know what's causing what in this case. You just know that there is a relationship between them, right? And that's usually shown as a scatter plot. And by the way, the scatter plot, each of these individual units aren't necessarily related, right? Because each of these represents a car, right? Which is going to be completely independent of the others. So just looking for a pattern. So these are some of the things that I expect you to always have in when you do graphs. So you make sure that you include a title, label the axis, so what did the x-axis represent and what the y-axis represents. Make sure you include the units. I will always look for this. And then if it's have multiple lines or multiple color bars or something like that, you need to include a key to represent what each one of them is. Okay, make sure the tick marks on the axis is at regular intervals and equally spaced. So let me go back and show you. These values on both x and the y axis, they are equally spaced in terms of how much each of these spaces represents the same amount. So this is from here to here is $20,000. From here to here is another 20. From here to here is another 20. So here's another 20, right? And same thing up here. From here to here looks like it's 20 miles per hour. So each tick marks represents the same. It's equally spaced. And you also the size has to be the same as well. So that's why when we make graphs, we often use graph paper so we can make sure that these sizes are the same, and then the values needs to also be equally spaced as well, and that's very important. If you do these on a computer, it will automatically do it for you, but I am going to have you do some graphs by hand, so those are the things you need to keep in mind. Bar and line graphs, independent variable goes on the horizontal axis. So generally speaking, independent variable is on the x-axis. Sometimes you can have bar graphs that go sideways, in which case the independent variable is on the y-axis. But for the most part, independent variables go on the x-axis, and then label and the units for the dependent variable goes on the y-axis. If you're plotting two sets of data on a different scale, you can have a secondary. Yeah, there's sometimes you have a and this is what I meant by the sometimes the bar graph can be on its side. The secondary axis. So for example, this one has a secondary axis. So this is looking at, because you're looking at both area and depth at the same time, and they both, and you looking, you're comparing them between the different oceans here. Area has one unit and depth has another unit, so you can't put it on the same, you can't use the same numbers, and you can't use the same axis. So in this case, you have a secondary axis. Sometimes you might have a secondary axis if you're looking at something and they're completely different. So maybe different scale. Maybe you're looking at population of, rabbits, and then also population of bacteria or something like that. So the number of rabbits might be in the hundreds, and number of bacteria might be in, in the millions or something like that, in which case you can't put it on the same axis, so you have a secondary axis for that. And then after you have analyzed your data, you draw some conclusions. You might need to use some mathematical tools, some statistics to prove or show that your data actually makes sense and that supports your hypothesis. And repeating experiments is actually another very important part of the scientific process. You yourself might do the repeating, or it could be somebody else doing an experiment. Repeat an experiment and try to confirm your results. Okay, maybe you might try it in with a different location or different different situations. But it's important to confirm the results you got in different ways. And the final part of the scientific method is communication. Communication is really important in science because science builds on itself, right? So science builds on other sciences. So if you don't communicate and make what you found out known, then other people can't learn from it. So whether your experiment worked or not, it's really important to communicate that, so that other people know what has been done and what hasn't been done. What are some of the what is the understanding of the science right now, so they can move forward. Right? And these are generally done. Scientists have their own little peer-reviewed journals that they publish. They also do presentations at conferences and things like that in front of other scientists. So those are some of the ways in which scientists communicate.